supernovae. I mean, the word itself just screams cosmic drama, doesn't it? Stars exploding, just spectacularly.
Yeah, they briefly outshine whole galaxies. It's incredible.
But beyond just the amazing visuals, these events are, wh- they're absolutely fundamental to how we understand the universe.
They really are. It's fascinating how these, violent deaths of stars link up to so many different areas: star formation, galaxy evolution.
Even the expansion of the cosmos itself.
Exactly. It's all connected.
And that's what we're digging into today. This deep dive is all about what the Gaia mission, the star mapper, is showing us about supernovae based on some really cool science.
Right. And it's interesting that the initial hopes for Gaia, detection-wise, they were huge.
Yeah, wasn't it something like 100,000 supernovae they thought it might catch?
Initially, yeah. That number got revised down quite a bit later, more like 10,000.
Which kind of highlights the challenge, right?
Totally. Gaia sees a lot, but spotting a transient event like a supernova and then getting ground telescopes pointed at it quickly, that's tricky. You need that light curve.
Ah, the photometric light curve. How the brightness changes over time.
Exactly. That pattern tells you so much about the type of explosion it was. It's the trigger for the follow-up.
Okay, so our mission today isn't just counting. We want to get into the science coming out of Gaia's observations, the actual insights.
What we're learning, yeah. And we can basically break supernovae down into two main physical classes.
Thermal runaway and core collapse.
Those are the big ones. Different mechanisms, different stars involved.
Let's start with thermal runaway then. Type Ia. These are the smaller, older stars.
Often, yeah. Think white dwarfs in binary systems, usually. They pull material off a companion.
Or maybe merge with another white dwarf.
That, too. And they gradually gain mass, accumulate this material until, bang, critical point.
It's like a runaway nuclear furnace.
Pretty much. Unstoppable fusion reaction that just completely obliterates the star. Huge, bright explosion.
And the key thing here for us astronomers is how consistent they are.
Incredibly consistent. Their peak brightness is remarkably similar, event to event. That's why they're so valuable.
The standard candles.
Exactly. Allows us to measure vast distances across the universe.
And these standard candles, they basically led to the discovery of, well, the accelerating expansion of the universe.
Huge discovery. Totally changed cosmology. Can't overstate that.
So they help us map out that large-scale Hubble expansion.
Right, the general trend of galaxies moving apart. But the universe isn't perfectly smooth. There are clusters, voids.
Things aren't just moving straight out.
Exactly. There are these smaller scale streaming motions, galaxies moving relative to that smooth Hubble flow because of local gravity. To measure those, you need distance measurements independent of the expansion rate.
And type Ia supernovae give us that. Reliable cosmic mile markers.
Precisely. Super important tool.
Okay, let's switch tracks. Core collapse supernovae. These are the big guys, right?
Yeah.
Massive stars.
Yeah, much more massive, living fast and dying young, relatively speaking, 10 to maybe 100 times the mass of our sun.
And what happens is they burn through their nuclear fuel.
Right. The fusion in the core stops producing enough outward pressure to counteract gravity.
So the core just collapses.
Under its own immense weight, yeah, it implodes.
And that implosion can trigger the outward explosion we see.
It often does. A shockwave blasts the outer layers off. That's your type 2 or IBC supernova. But sometimes.
Sometimes it doesn't.
Sometimes the collapse just continues. If not enough energy is released outwards, the core collapses directly into a neutron star or even a black hole without a really bright visible supernova.
And what determines the outcome? Is it just the mass?
Mass is key, definitely, but also its metallicity, the amount of heavier elements it started with. Those factors influence which specific type of core collapse event you get.
So these aren't just explosions. They're like extreme physics labs.
Oh, absolutely. The conditions inside density, temperature are unimaginable. It's where really exotic stuff forms.
Like neutron stars, black holes.
Millisecond pulsars, those super fast spinning neutron stars, maybe even some gamma ray bursts.
Wow. And they're sources of other fundamental things too.
For sure. We know they produce gravitational waves, those ripples in space-time. They blast out neutrinos, high-energy cosmic rays.
And they mess with binary systems too, I imagine.
Big time. They really shape the evolution of interacting binaries where stars are close enough to swap material. They're probably involved in forming things like low-mass X-ray binaries.
And those weird X-ray sources in globular clusters.
Yeah, thought to be linked. The dynamics are complicated, but supernovae play a role.
Okay, zooming back out again, what's their galactic impact? Big picture.
Oh, fundamental, absolutely fundamental. They are the main factories for heavy elements.
Everything heavier than hydrogen and helium, basically.
Pretty much. Carbon, oxygen, iron, all the stuff needed for planets, for life. They forge it in the core and during the explosion, and then
Blasted out into space.
exactly, enriching the interstellar medium, providing the raw materials for the next generation of stars and planets. You can see their chemical signatures in galaxy clusters, even in the gas between galaxies.
So they're cosmic recyclers and builders. That's amazing. You also mentioned the rate of supernovae tells us something.
Yeah, about star formation history. It's a neat probe.
How does that work?
Well, core collapse supernova come from massive stars, and massive stars don't live very long, cosmically speaking.
Right, millions of years, not billions.
So the rate of type 2 supernovae, for example, is pretty much directly proportional to the current rate of massive star formation in a galaxy. Lots of massive stars forming now means lots of type 2s soon after.
Okay, that makes sense. What about type Ia?
They come from older, lower mass stars, white dwarfs and binaries. It takes time for those systems to evolve to the point of explosion.
So the rate isn't tied to now.
It reflects more of the integrated star formation history over a longer period. It's like a convolution of past star formation activity.
Got it. Okay, that's a great overview. Now let's get to
Yeah.
Gaia. What specifically is it adding to this picture? Sounds like its precision is the key.
Absolutely. Gaia's astrometry measuring positions and motions with insane accuracy is the game changer. One big area is just getting much better distances.
To the remnants, the debris
And
class.
the stars involved, yeah. Using parallax, that tiny apparent shift in a star's position as Earth orbits the sun, Gaia measures that incredibly well.
Can you give an example?
The Cygnus loop, beautiful remnant. People used Gaia's EDR3 data, looked at stars showing signs of interacting with the shockwave.
And that let them pin down the distance.
Yeah, really precisely. To 725 parsecs, plus or minus only about 15. That's tighter than the size of the remnant itself. Helps you figure out the real size, energy, age.
Wow, that kind of accuracy must make a huge difference. Any others?
Well, the Vela complex around the Vela pulsar, researchers used like 18 million stars from Gaia over a huge patch of sky.
18 million.
Yeah, and it revealed this incredibly detailed 3D map of the cavity blown by that old supernova. And then there's Tycho supernova from 1572.
It's a famous one.
Right. Gaia data is giving us the best look yet at the distances and movements of stars that might have been its companion before it blew up.
So Gaia helps map the aftermath and gives clues about the stars before the explosion, the progenitors.
Exactly. Combine Gaia's data with simulations, and you start to piece together what kind of star blew up. It's like cosmic forensics.
Like solving the crime.
Right.
What about the Vela pulsar's progenitor? You mentioned the remnant.
Right. A study looked at bright stars nearby using Gaia, trying to figure out what kind of star exploded to make the pulsar.
Mm-hmm.
They estimated a surprisingly low mass, actually. Maybe only 8 to 10 times the sun's mass.
Which is low for a core collapse supernova, isn't it?
It is, yeah. Suggests maybe neutron stars can form from a slightly wider range of stars than we thought.
Interesting. And for type Ia, any progenitor clues?
Well, deep imaging of SN 1972e, that was the nearest type Ia in ages, combined with Gaia constraints, has helped rule out some popular ideas. Like the idea that the companion star feeding the white dwarf was always a helium star or a really bright main sequence star. The picture's getting clearer, but also more complex.
So studying the surroundings remnants, potential survivors, helps reconstruct the before.
Yeah.
Cosmic archaeology, like you said.
Yeah.
You mentioned fast-moving stars, too. Forensic tool.
Yeah, that's a cool angle. Stars moving really, really fast can sometimes be traced back to a violent event.
Like being kicked by a supernova.
Exactly. Shen and collaborators found 3 hypervelocity white dwarfs using Gaia DR2, moving at like 1,000 to 3,000 kilometers per second.
Whoa.
And their paths suggest they were likely companions in type Ia systems. The explosion shattered the binary and flung the white dwarf survivor outwards at incredible speed.
Blasted out like shrapnel. Was there something about an X-ray binary, too? A runaway?
Yeah, HD 153919 4U 1737. It's an X-ray binary moving pretty fast. Using Gaia EDR3, researchers traced its motion back.
Back to where it was born.
Seems like it. Back towards the SCO-OB1 association, a group of young, massive stars. The idea is a supernova happened in a close binary within that association.
And the kick from the explosion sent this remaining binary system flying.
Exactly. Ejected it. And what's really interesting is their modeling suggests the star that went supernova was really massive, over 60 solar masses.
And it likely formed a neutron star.
Probably. And this kind of system, a massive star exploding in a close binary, leaving a compact object, might be a channel for forming things we see in gravitational waves.
Like merging black holes or neutron stars?
Potentially, yeah, like that event GW 190412, which had unequal mass black holes. This runaway binary could be a prototype for how you get systems like that. Gaia is connecting supernovae to gravitational wave sources.
That's a huge connection. What else? Something about neutron star speeds, their birth kicks.
Right. Yang and colleagues did a statistical thing. They took young pulsars, where we have good distance measurements from radio observations, and looked at their velocities.
How fast they're moving through space.
Yeah. And they compared those speeds to nearby normal stars measured by Gaia DR2.
And the result?
They found the sort of sideways motion, the transverse velocity of these young pulsars is pretty comparable to the overall speed range of older local pulsars. And it implies those initial kicks they get when they're born in the supernova.
Yeah.
They're significant. They're a major factor in the pulsar's final velocity, not just the motion inherited from the progenitor star or binary system. These kicks really matter for binary evolution, too.
Makes sense.
Mhm.
A big kick could unbind a binary system entirely. Which brings us to, how many progenitors are in binaries when they explode?
Crucial question, especially for predicting merger rates for LIGO and Virgo. Kochenek did a search using Gaia EDR3, looked around 10 supernova remnants that have a neutron star or black hole inside. Any surviving companion stars that got kicked away but weren't completely lost, unbound binaries or triples.
Find any?
They confirmed one known case, HD 37424, linked to a specific pulsar. But the bigger picture, combining this with other work, it's kind of surprising.
How so?
It looks like maybe around 70%, a big majority of stars that form neutron stars via supernovae were actually single stars when they exploded, not in binaries.
Really? That seems high.
It does, yeah. Then maybe 15% produce bound binaries that survive, and about 10% make unbound ones, like HD 37424.
So most core collapses might be from single stars.
Yeah.
Interesting. Tell me about that confirmed one, HD 37424. What's its story?
It's a good illustration. The star that blew up to make the pulsar, PSR J0538 plus 2817, was probably fairly massive, maybe 13 to 19 solar masses.
Okay.
Before it exploded, it likely swelled up and started dumping mass onto its companion. HD 37424 reached its Roche lobe.
Filled its gravitational boundary.
Right. Then the Type 2 supernova happened, the explosion disrupted the system, and HD 37424 went flying off, no longer bound to the newborn neutron star.
A very dramatic breakup.
Okay.
Thinking about other dramatic things.
Yeah.
Black holes, LIGO, Virgo, KGRA are seeing merging black holes. Is Gaia helping find black holes too?
Well, that's the hope, and there's definitely potential. Those gravitational wave detections have really spurred interest in finding stellar mass black holes in our own galaxy.
We think there are tons of them, right?
Billions.
Billions.
Estimates vary wildly, but yeah, potentially a huge population. But they're dark. Hard to see directly unless they're actively feeding on a companion star and emitting X-rays. We've only found maybe 60 or so that way.
So how does Gaia help find the quiet ones?
Through astrometry again. The idea is to look for seemingly normal, bright stars that are actually orbiting an unseen black hole, a detached binary.
No mass transfer, so no X-rays.
Exactly. But the luminous star is still orbiting this invisible heavy companion. Gaia might be precise enough to see the tiny wobble in the visible star's position as it orbits the black hole.
Like seeing a dog walker being pulled by an invisible dog on a leash.
That's a great analogy, yeah. You infer the presence of the unseen mass from its gravitational effect on the visible star.
Clever. Have people run simulations? How many might Gaia find?
Tall and colleagues did. Their simulation suggests that over its full 10-year mission, Gaia might detect maybe 30 to 300 of these black holes in detached binaries.
That would be amazing.
It would be huge, especially systems with orbital periods less than about 10 years, which Gaia is sensitive to. It would give us real observational constraints on how these binary systems evolve to produce merging black holes.
So it really feels like everything we've talked about, all these Gaia results,
Yeah.
it's just scratching the surface.
Oh, absolutely. This is just the beginning. We're tapping into a really rich new seam of observational data here. Gaia is enabling whole new ways to study these events.
It's setting the stage for the next big leaps in understanding, isn't it? Figuring out the progenitors, the explosion details, the remnants.
It really is.
Huh.
Which kind of leads to a final thought, something for you, the listener, to chew on.
Okay.
As we get all this incredible new data from missions like Gaia, think about how it's constantly reshaping our picture. Our understanding of how stars live and die, how galaxies get built up, even the basic fabric of the universe.
Yeah.
It's always evolving.
Yeah. So what other surprises might be hiding in the Gaia data? What totally unexpected things might we learn about supernovae next?